Welcome to Ultimate Sleep Doctor. Tonight, we'll journey to a place of profound quiet. Deep beneath the waves in the ocean's abyss lies a world unlike any other. It's a realm of perpetual darkness, of immense pressure, and of creatures adapted to thrive in conditions that seem utterly alien. Scientists are constantly uncovering astonishing facts about this unexplored territory. Secrets held by bioluminescent jellyfish, colossal squid, and ecosystems built around hydrothermal vents. Consider the stillness of the deep, a place where the surface world's worries gently fade. It's a reminder that even in the vastness of space and time, there is a quiet beauty waiting to be discovered. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift, like the currents of the deep. Let's begin. The ocean holds countless secrets, but the deepest secrets reside in a realm far removed from sunlight and familiar life. We're going to journey to the Hadal Zone, the deepest parts of our planet's oceans. These aren't just deep. They represent a world of extreme conditions, a place where the pressure is immense, the temperature is perpetually cold, and human exploration faces incredible challenges. The Hadal Zone is defined as the depths below 6,000 meters. That's roughly 20,000 feet. It's broken down into three distinct zones: the Abyssal Zone, extending from 3,000 to 6,000 meters, the Hadal Zone from 6,000 to 11,000 meters, and the Ultra-Abyssal Zone beyond 11,000 meters. Most of the research and discovery we've made so far has been within the Hadal Zone, particularly in the deepest trenches of the Pacific Ocean. Let's talk about pressure. As you descend into the ocean, the weight of all the water above you increases dramatically. At sea level, the pressure is about 1 atmosphere. For every 10 meters you descend, the pressure increases by 1 atmosphere. In the Hadal Zone, the pressure at the bottom of the Mariana Trench, the deepest point on Earth, is over 1,000 times greater than the pressure at sea level. That's equivalent to having 50 jumbo jets stacked on top of you. This immense pressure isn't just a number. It's a force capable of crushing most materials. Specialized submarines and remotely operated vehicles, ROVs, are built with incredibly strong materials, often titanium, to withstand these forces. The temperature in the Hadal Zone is consistently near freezing, typically around 1 to 4 degrees Celsius, 34 to 39 degrees Fahrenheit. This coldness is due to the lack of sunlight and the insulating effect of the deep water. There's no heat from the sun to warm the water. The cold also plays a crucial role in the density of the water, further contributing to the extreme pressure. Exploring the Hadal Zone is a monumental technical undertaking. Traditional submarines simply cannot survive the crushing pressure. Instead, scientists rely on ROVs, unmanned vehicles equipped with cameras, sensors, and robotic arms, and autonomous underwater vehicles, AUVs, which can operate independently for extended periods. These vehicles are tethered to a surface ship, allowing scientists to control them and transmit data back to the surface. The challenges are immense. Communication signals don't travel well through deep water, navigation is difficult, and the potential for equipment failure is high. Despite these obstacles, researchers are beginning to uncover remarkable things about life in the Hadal Zone. Scientists have discovered unique ecosystems thriving around hydrothermal vents, fissures on the seafloor that release superheated, mineral-rich water. These vents support chemosynthetic bacteria, which form the base of the food chain, and in turn, harbor specialized creatures like amphipods, snailfish, and even giant isopods. It's a testament to life's tenacity and adaptability, a truly remarkable corner of our planet. The ongoing exploration of the Hadal Zone promises to reveal even more about the mysteries of the deep ocean, challenging our understanding of life and the planet we call home. The crushing darkness of the abyss isn't simply empty. It's teeming with life, a hidden world illuminated not by the sun, but by its own light. This incredible phenomenon, called bioluminescence, is perhaps the most enchanting aspect of deep-sea exploration. It's essentially the production and emission of light by living organisms, a natural flashlight, if you will, produced within their bodies. The mechanisms behind this light show are fascinating, and they vary slightly between species. At its core, bioluminescence relies on a chemical reaction. Most deep-sea creatures use a molecule called luciferin, which reacts with oxygen, often catalyzed by an enzyme called luciferase. Think of it like a tiny, self-contained sparkler. Different luciferins create different colors of light. Blues and greens are the most common in the deep ocean because they travel farthest in water, while reds and yellows are rarer. Some organisms, like certain jellyfish, utilize bacterial symbiosis, keeping colonies of bioluminescent bacteria within their bodies, essentially hosting living light sources. The functions of bioluminescence are incredibly diverse. One of the most common is attracting prey. Many anglerfish, for instance, possess a bioluminescent lure, a modified dorsal fin spine that dangles in front of their mouths, enticing smaller fish to swim closer, becoming an easy meal. Another critical use is defense. Some species, like certain shrimp, emit a sudden flash of light when threatened, startling predators and allowing them to escape. This burglar alarm effect is surprisingly effective in the inky blackness. Furthermore, bioluminescence plays a vital role in communication. Some deep-sea worms use flashing patterns to signal to potential mates, creating a spectacular underwater light show. Others utilize it to coordinate group behaviors, like schooling or defense. The precise details of these light-based conversations are still being researched, and scientists are only beginning to understand the complexity of this communication system. Let's take a closer look at some of the iconic creatures that utilize this ability. The viperfish, with its needle-sharp teeth and lure, relies heavily on bioluminescence to ambush its victims. The hatchetfish, a small, flattened fish, produces a shimmering glow along its underside, using it to camouflage itself against the faint, downward-spreading light from above, a form of counter-illumination. Even the colossal squid, a truly enormous and mysterious creature, is believed to use bioluminescence for a variety of purposes, including attracting prey and possibly confusing predators. Scientists have captured footage of these magnificent animals emitting bright flashes, revealing a level of complexity in their behavior that was previously unimaginable. The study of bioluminescence in the deep sea is continually revealing new secrets, highlighting the incredible adaptability and ingenuity of life in the most extreme environments on our planet. It's a reminder that even in the darkest corners of the ocean, there is beauty, complexity, and a remarkable display of natural wonder. Far below the sunlight's reach, where the pressure is immense and the temperature is perpetually cold, a truly remarkable world exists the realm of hydrothermal vents. These aren't just cracks in the ocean floor, they are gateways to incredibly vibrant and self-sustaining communities. The foundation of this life isn't sunlight, as you might expect, but rather chemistry. Scientists call this process chemosynthesis. It's similar to photosynthesis, where plants use sunlight to create energy. But instead of light, chemosynthetic organisms harness the power of chemicals, primarily hydrogen sulfide released from the vents. The vents themselves spew out superheated water, rich in minerals dissolved from the Earth's crust. As this hot, mineral-laden water mixes with the cold, surrounding seawater, it creates a chemical gradient, a difference in concentration that fuels the chemosynthetic process. Tiny bacteria and archaea, single-celled organisms, thrive in this environment, consuming the hydrogen sulfide and other chemicals to produce energy and, crucially, to build organic matter. These bacteria form the base of the food chain, supporting a complex web of life. The communities around these vents are astonishingly diverse. Giant tube worms, like the Riftia pachyptilla, are perhaps the most iconic examples. These worms lack a mouth or digestive system entirely, relying entirely on bacteria living inside their tissues to perform chemosynthesis. Other creatures, including shrimp, crabs, and mussels, have evolved to live in close association with the vents, feeding directly on the bacteria or consuming the animals that graze on them. Some species even have specialized immune systems to cope with the toxic chemicals released by the vents. Perhaps the most groundbreaking discovery linked to hydrothermal vents was the identification of archaea. Initially, scientists believed that all chemosynthetic organisms were bacteria. However, research conducted in the 1980s, spearheaded by scientists like Kenneth Nielsen and J. William Skopf, revealed a completely new branch of life, the archaea. These single-celled organisms were found to be the primary drivers of chemosynthesis at many hydrothermal vents. Archaea are fundamentally different from bacteria and even from eukaryotes, organisms with a nucleus, like plants and animals. They possess unique cell structures and genetic makeup. The discovery of archaea revolutionized our understanding of the origins of life on Earth. It suggested that life might have originated in these harsh, chemically rich environments, independent of sunlight. Furthermore, the study of archaea at hydrothermal vents has implications far beyond Earth. Scientists believe that similar chemosynthetic ecosystems might exist on other ocean worlds, moons like Europa or Enceladus, where liquid water oceans are thought to exist beneath icy surfaces. These environments could potentially harbor life, sustained by the same chemical processes that thrive around hydrothermal vents here on our own planet. The continued exploration of these deep-sea communities is a testament to the incredible adaptability of life and the enduring mysteries that remain hidden within the deepest corners of our world. It's a reminder that even in the most extreme environments, life finds a way. The blackness of the deep ocean presses in on everything, a constant, invisible weight. But the fish that call this place home aren't crushed by it. Instead, they've evolved remarkable strategies to thrive in this extreme environment. One of the most fascinating adaptations is their ability to handle immense pressure. Fish living at depths of several thousand meters have bodies structured differently than those closer to the surface. Their bones are often more cartilage-based, far lighter and more flexible. This reduced skeletal density allows them to absorb the crushing pressure without shattering. Furthermore, Their cell membranes are packed with special lipids, fats, that maintain their fluidity, preventing them from becoming rigid and brittle under the intense pressure. These lipids essentially act like tiny shock absorbers, ensuring vital cellular processes continue smoothly. Beyond pressure, the deep sea presents a significant challenge to vision. Sunlight simply doesn't penetrate to these depths. Consequently, most deep-sea fish have lost their ability to see color. Instead, they've evolved incredibly sensitive eyes that are adept at detecting the faintest traces of light, often in the blue-green spectrum. Some species, like the anglerfish, have developed a truly unique adaptation, a bioluminescent lure. This dangling light source, produced by symbiotic bacteria, acts like a beacon, attracting unsuspecting prey in the complete darkness. The light itself isn't seen in the same way as light from the sun. It's detected by specialized cells within the fish's eye, incredibly sensitive to the photons emitted by the bacteria. Metabolism in the deep sea is a delicate balancing act. Food is scarce at these depths, and energy conservation is paramount. Many deep-sea fish exhibit a remarkably slow metabolic rate, allowing them to survive for extended periods without feeding. They've developed specialized enzymes and biochemical pathways that are incredibly efficient at converting food into energy, minimizing waste. Some species, like the vampire squid, can enter a state of suspended animation, drastically reducing their metabolic activity and conserving energy until a meal presents itself. Finally, let's consider the senses of deep-sea fish. While vision is diminished, other senses are heightened. Lateral lines, a network of pores running along the fish's body, are extraordinarily sensitive to vibrations in the water. These vibrations can detect the movement of prey, the approach of predators, or even subtle shifts in the currents. Many deep-sea fish also possess highly developed olfactory senses, capable of detecting incredibly faint chemical signals, pheromones, released by potential mates or food sources. Some species even appear to hear by detecting the sounds produced by other animals. Although the acoustic environment at these depths is often incredibly complex and noisy, dominated by the rumble of tectonic plates and the calls of marine mammals. The adaptations of these deep-sea fish are a testament to the power of evolution, demonstrating how life can flourish even in the most extreme environments. Their survival depends on an intricate interplay of physiological strategies, a silent symphony of pressure tolerance, enhanced vision, efficient metabolism, and exquisitely tuned sensory systems. The quest to understand the ocean's deepest secrets began with audacious dreams and remarkably fragile vessels. Early attempts to reach the abyssal plains relied on bathyscaphs, truly remarkable machines designed to defy the crushing pressure of the deep. These pioneering craft, like the Trieste, piloted by Jacques Piccard and Swiss oceanographer Don Walsh, were constructed primarily of steel and glass, offering a breathtaking, if precarious, view into the Hadal Zone for the first time in recorded history. The Trieste's mission in 1963, documenting the Challenger Deep in the Mariana Trench, was a monumental achievement, providing the first photographic evidence of this immense, unexplored environment. However, the inherent instability of the spherical design, coupled with limited battery power and reliance on helium for buoyancy control, meant that bathyscaphs were inherently risky operations. As technology evolved, engineers sought more robust and controllable solutions. remotely operated vehicles, or ROVs, emerged as a game changer. Unlike manned submersibles, ROVs are tethered to a surface vessel via a cable, providing power, communication, and control. These machines, equipped with sophisticated cameras, manipulators, and sensors, quickly surpassed bathyscaphs in terms of operational duration and data collection capabilities. Modern ROVs, such as the Nereus, designed by Woods Hole Oceanographic Institution, demonstrated the ability to explore previously inaccessible regions, collecting samples and conducting detailed surveys of the seafloor. They aren't piloted in the same way as a human submersible. Instead, operators on the surface control the ROV's movements and instrument readings in real time. The development of manned submersibles has also continued, though with a greater emphasis on safety and endurance. Current designs, like the Alvin, operated by the Woods Hole Oceanographic Institution, incorporate advanced materials, titanium and ceramics, to withstand extreme pressures. These submersibles are also equipped with sophisticated navigation systems, powerful lighting, and robotic arms for collecting samples. Importantly, they include redundant systems and emergency ascent mechanisms, drastically improving safety compared to earlier designs. Furthermore, advancements in propulsion systems, using electric motors and vectored thrusters, provide unprecedented maneuverability, allowing submersibles to navigate complex underwater terrain and conduct detailed investigations. These submersibles are frequently deployed to study hydrothermal vents, examine deep-sea ecosystems, and even search for lost shipwrecks. The ongoing development of autonomous underwater vehicles, AUVs, capable of operating independently for extended periods, promises to further revolutionize deep-sea exploration, opening up even more possibilities for scientific discovery. The future of deep-sea research rests on a sophisticated combination of these technologies, each building upon the successes and lessons learned from previous generations of deep-sea explorers. The deep ocean, already a place of incredible strangeness, holds another profound secret: vast deposits of methane hydrates. These aren't glittering jewels, but rather a frozen form of natural gas, and their existence dramatically reshapes our understanding of the Earth's chemistry and potential future. Methane hydrates are essentially methane, the same gas we use to heat our homes, trapped within a crystal lattice of water. It's like tiny ice skaters holding hands in a perfect circle, with the methane nestled within. These structures form under specific conditions, immense pressure and cold temperatures. They're most commonly found on the continental slopes and rises of oceans around the world, particularly in areas with thick sediment. Scientists believe they're created when marine organisms, like certain bacteria and archaea, the same fascinating life forms we discussed in the vents, consume organic matter sinking from the sunlit surface waters. This consumption generates methane as a byproduct. The methane then gets trapped as the water surrounding it freezes, forming the hydrate crystal. It's a continuous cycle, driven by the flow of organic carbon. The sheer scale of these deposits is astonishing. Estimates suggest that the oceans contain far more methane hydrates than are currently known, potentially locked away for millions of years. They represent a massive reservoir of energy, a fuel source waiting to be unlocked. Geologically, the presence of methane hydrates has significant implications. They offer clues about the Earth's past climate. During warmer periods, when sea ice melted and water circulated more freely, methane hydrates could have been released into the atmosphere, acting as a potent greenhouse gas, far more so than carbon dioxide. Studying their distribution and stability helps scientists reconstruct ancient climate conditions and better understand the drivers of climate change. However, the potential release of methane hydrates isn't just a story of the past. Scientists are increasingly concerned about the possibility of them destabilizing in the future due to warming ocean temperatures. If the water surrounding these hydrates warms, the pressure balance shifts, and the methane can escape, forming bubbles in the water, a process known as methane bubbling. These bubbles can dramatically alter marine ecosystems, disrupting the habitats of deep-sea creatures. More worryingly, released methane can rise into the atmosphere, contributing to global warming. The exact mechanisms and rates of this potential release are still being investigated, but ongoing research is crucial. Models are being built to predict how warming temperatures might trigger a large-scale release, and understanding the factors that control hydrate stability, things like sediment composition and ocean currents, is a top priority. It's a complex and challenging puzzle, a reminder of the interconnectedness of our planet's systems. The ocean's depths hold secrets, and increasingly they hold the promise and the potential peril of deep-sea mining. For centuries, we've extracted resources from the seafloor, but until recently, the extreme pressures and vast distances made large-scale operations incredibly difficult. Now, technological advancements, particularly in robotics and autonomous vehicles, are opening a new chapter in this story. Several companies are actively developing plans to exploit the resources hidden beneath the waves, primarily focusing on polymetallic nodules, dense, potato-shaped rocks scattered across the abyssal plains. These nodules contain valuable metals like manganese, nickel, copper, and cobalt, elements increasingly vital for batteries, electronics, and other technologies. These mining operations aren't about simply scooping up nodules. Proposals involve using specialized remotely operated vehicles, ROVs, to excavate the nodules, then transporting them to surface vessels for processing. The Seabed Resources Exploration and Exploitation Company, SREC, for instance, is currently conducting a systematic survey of the Clarion-Clipperton Zone in the Pacific, a region rich in polymetallic nodules. Other companies are pursuing similar ventures in areas like the Indian Ocean and the Atlantic. The technology being developed relies heavily on sophisticated sensors, navigation systems, and robust construction to withstand the immense pressures, over 500 times that at sea level, and the challenging currents of the deep. However, the prospect of extracting these resources raises serious concerns about the potential environmental impact. The abyssal plains are home to unique and fragile ecosystems, many of which haven't even been fully mapped or understood. Mining operations could destroy vast areas of seabed habitat, disrupting the lives of many deep-sea creatures, including giant clams, sea cucumbers, and the elusive anglerfish. The disturbance isn't just physical. The plumes of sediment stirred up by mining could smother filter-feeding organisms and disrupt the delicate balance of the food web. Furthermore, the process releases stored carbon, previously locked away in the sediments for millennia. Scientists are still studying the extent to which this released carbon will contribute to climate change, though initial research suggests it could be a significant factor. There's also the issue of the ghost fishing effect. the mining equipment itself could act as a long-term source of pollution, attracting and potentially trapping marine life. The regulatory framework surrounding deep-sea mining is still in its early stages. The International Seabed Authority, ISA, is responsible for overseeing these activities, but its rules are currently being developed. A key challenge is balancing the demand for critical minerals with the need to protect these largely unexplored and potentially vulnerable environments. There's an ongoing debate about establishing stringent environmental standards, including mandatory impact assessments, monitoring protocols, and, crucially, the establishment of marine protected areas. Looking ahead, the future of deep-sea mining hinges on innovation, both technological and regulatory. Research into more targeted extraction methods, minimizing sediment plumes, and developing robust monitoring systems will be critical. The scientific community is actively working to better understand the deep-sea ecosystems and assess the long-term consequences of mining. Ultimately, the decision of whether and how to proceed with deep-sea mining will require a careful and considered approach, one that prioritizes the health of our oceans alongside our technological needs. It's a complex puzzle, and the solution will shape the future of the deep. The deep ocean isn't a silent place, not really. It's a place brimming with sound, a vast and complex orchestra unlike anything we experience on land. Scientists studying this acoustic ecology of the abyss are discovering a world of incredible communication and behavior hidden beneath kilometers of water. The pressure at these depths is so immense that sound travels differently, much faster and further than it does in air. A single whale song, for example, can travel hundreds, even thousands of miles across the ocean, carried by the speed and intensity of sound waves. Researchers utilize specialized equipment called hydrophones, underwater microphones, to record these sounds. These aren't your typical microphones. They're built to withstand the crushing pressure and are often remotely deployed via cables connected to research vessels. The signals captured are incredibly faint, often buried within a tremendous amount of noise. The ocean itself is a noisy environment filled with currents, turbulence, and the sounds of marine life. Many deep-sea animals rely on sound for nearly every aspect of their lives. Some, like the colossal squid, are thought to use low-frequency calls to locate mates over vast distances. These calls are so powerful that they can be detected by hydrophones thousands of meters away. Other creatures, such as anglerfish, utilize a distinctive humming sound to attract prey. The exact mechanisms of these sounds and how they're produced and received are still being actively investigated. Scientists are starting to understand that the sounds aren't just about attracting food. They're critical for navigation, social interactions, and territorial defense. A fascinating area of study involves the sounds produced by invertebrates. Scientists have recorded distinct clicking and buzzing sounds from shrimp, crabs, and even sea cucumbers. These sounds likely play a role in communication and potentially even in sensing their surroundings, perhaps detecting the vibrations of prey or predators. The study of these subtle sounds is proving surprisingly complex, requiring incredibly sensitive recording equipment and sophisticated data analysis techniques. However, capturing the acoustic environment of the abyss presents enormous technical challenges. The immense pressure can distort sound waves, making it difficult to accurately record and interpret the data. Equipment malfunctions are common. and the long cable connecting the hydrophone to the research vessel is susceptible to damage from currents and marine life. Furthermore, accurately pinpointing the source of a particular sound, determining whether it's a whale, a shrimp, or a geological event, is exceptionally difficult. Algorithms and advanced sonar technology are being developed to help researchers isolate and identify individual sounds within the overwhelming cacophony of the deep. Recent advances include the use of autonomous underwater vehicles, AUVs, equipped with hydrophones, allowing for longer-term monitoring of specific areas. These AUVs can be programmed to follow certain creatures or track specific sound events, providing a more detailed and dynamic picture of the acoustic landscape. The ongoing exploration of the deep sea is revealing a world of astounding sonic complexity, hinting at a hidden ecosystem far more vibrant and interconnected than we previously imagined. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds one peaceful night at a time. The mysteries of the ocean abyss now gently recede, their silent wonders held within your mind. Let your thoughts drift, calm and unhurried, like currents in the deep. Allow your body to surrender to a quiet release. Good night.